Gases and chemical reactions. So sometimes we do a chemical reaction and the reactants might be gases or the products might be gases. And so we can look at stoichiometry and deal with the gases by using the ideal gas law. So if we have the volume, the temperature, and the pressure of the gas, we can find the moles of gases. And so this is a variation on stoichiometry. We had grams to moles to grams, right? Well, now if, say, we've got that magnesium and hydrochloric acid reaction going on, instead of getting a mass of product, we might get a gas, and we'll get a volume, a temperature, and a pressure. Okay? Or it could happen at the beginning that you're starting with a volume, pressure, and temperature. You can use PIV-NERT, the ideal gas law, to convert to moles. Let's do an example. In this reaction, 4.58 liters of oxygen were formed at 743 millimeters of mercury and 308 Kelvin. How many grams of silver oxide decomposed? So I'm going to revert back to what we did with stoichiometry and write the information below the balanced chemical equation. So they're telling me there's 4.58 liters of oxygen at 745 millimeters of mercury and 308 Kelvin. That's all pertaining to the oxygen. And then the question is, how many grams of silver oxide were decomposed? Well, this is what we're finding, and this is what we're starting with. Could we take this information, volume, pressure, and temperature, and find the number of moles of oxygen? Yeah, we could. If we get moles of oxygen, then we can get moles of silver oxide, and then from moles of silver oxide, we can go to grams. So we've got P, V, and T for the oxygen. We're going to go to moles, and then to moles of the silver oxide, and then to grams of silver oxide. So we're going to use PIV-NERT. Are these all good units for PIV-NERT? So millimeters of mercury work with 0.0821 liter atmospheres per mole Kelvin. No, it doesn't. So we need to convert that. So 745 is going to be divided by 760. It's going to come out, that's going to be equivalent to 0.98026, 3 sig figs atmospheres. PV equals nRT, so N equals PV over RT. So the pressure, 0.98026 atmospheres. The volume was 4.58 liters. Dividing by R, 0.0821 liter atmospheres per mole Kelvin times the temperature of 308 Kelvin. .98026 times 4.58 divided by 0.0821 divided by 308. 0.17755. This should have 3 sig figs, moles of got oxygen. So we just got to this point. We need to get moles of oxygen to moles of silver oxide. So moles Ag2O per mole O2. Where do we get the numbers for this conversion factor? Balanced chemical equation. 1 mole of oxygen from 2 moles of silver oxide. And then I need to convert this to grams of silver oxide. And where do we find that number? We use the periodic table. Silver, 107.9 times 2, plus oxygen, 16. So we get 231.8. So I've got 0.17755 times 2 times 231.8 equals, and this should have 3 sig figs, 82.3 grams of silver oxide. Any questions? When you're comparing gases, because they change so much with temperature and pressure, it can be confusing. And so scientists have established something called standard temperature and pressure, abbreviated STP. And this is 0 degrees Celsius, which is the same as 273 Kelvin, and 1 atmosphere. 1 atmosphere is just normal atmospheric pressure. 0 degrees Celsius is the temperature of an ice water bath. So it's very easy to get something to 0. You don't even need electricity or anything. You can just get an ice water bath and stick your container in it, it'll be at 0. So let's calculate the volume of 1 mole of gas at STP. So this is telling us the temperature, there's the pressure, here's the number of moles, we can calculate volume. PV equals nRT. So volume equals nRT divided by P. N is 1 mole. R is what it always is. Looks like latum mulc. Temperature, 0 degrees Celsius, but we have to use Kelvin. And 1 atmosphere. And that comes out to 22.4 liters. This has a special name. It's the molar volume of a gas at STP. 22.4 liters per mole. It's a very useful conversion factor. We actually have a block that's in the other lab. It's about this big, 22.4 liters. That's 1 mole of a gas. It doesn't matter which gas it is. It could be helium or hydrogen or argon or carbon dioxide, doesn't matter. The volume of the gas will be the same. And so we can use this as a conversion factor between volume at STP and moles of gas. 1 mole of any gas occupies 22.4 liters at STP because the size of the particles doesn't matter. There's so much space in between. The particles can be twice as big. It doesn't matter. That does change the mass of the gas. A mole of helium weighs 4 grams. A mole of xenon weighs 131 grams. It's a lot more, but they'll occupy the same volume because it's mostly empty space. How many liters of oxygen at STP are required to form 10.5 grams of water? We'll do this one really quick. 10.5 grams of water. How many moles of oxygen? No. How many liters? So this is going to be grams to moles to liters. 10.5 grams of H2O. We need to get to moles of H2O. It's 18.02. And then moles of oxygen per mole of water. What's the relationship? 1 mole of this to 2 moles of that. 1 to 2. And then 22.4 liters per mole. .5 divided by 18.02 divided by 2 times 22.4. 6.53 liters of oxygen. Any questions? You can only use it at STP. Yes, we finished. I'll see you on Thursday. We are doing a lab. Don't forget your lab coats.